Okay, really important application of linear relationships, so straight lines, is in direct proportion. Because in the real world, a lot of times two quantities will vary directly. So a classic example would be the time you're driving your car and the distance you drive. So as you drive for longer and longer and longer, you're going to travel further and further and further. And if you're travelling at a constant speed, you could graph time versus distance as a straight line. So we can use that for a lot of different problem type situations. So importantly, because you've got a straight line going through the origin, we know that it's got the formula y equals mx from last lesson. Now quite often, instead of writing m for slope, we'll put some k for what's called the constant of proportionality, and that's just something that links the two variables. So in that example where I was just talking about graphing time versus the distance you travelled, the gradient there would actually be the speed. So the gradient of the line would actually be the speed of the car. So this constant of proportionality, or the gradient, they're both the same thing. It's quite often got some sort of physical property from within the question itself. Okay, water is poured into an empty tank at a constant rate. So somebody's put a hose in there or a tap or something like that. It takes 3 hours to fill the tank with 6,000 litres. What is the rate at which water is poured into the tank? So the rate is simply going to be the amount of water that goes into the tank divided by the time it takes. So we get an answer of 2,000. And because we've divided litres by hours, that rate is going to be in litres per hour. Okay, part B, we're going to see the graph down here. So we start with an empty tank, and after 3 hours there's going to be 6,000 litres in the tank. Okay, now it's important we don't go past the 6,000 mark there, because presumably the tank's full, so even if we continue to put water in the tank, the line would go sideways there. So always have a think of the practical application. We don't always get all of a particular line. Okay, part C, find the gradient of your graph. So let's actually use the graph here. Okay, what we're going to find is it's equal to this thing here. Okay, so basically if we were to pick those 2 points there, again draw our little triangle in there. Now don't count squares here, because this isn't a one-to-one scale. You can see this side here is going from 0 up to 6,000. You can see this side here is going from 0 hours to 3 hours. So 6,000 divided by 3 is equal to that 2,000 number. You notice these happen to match these, but look, we could have picked any 2 points on there. We still would have got that same answer. Okay, part 2. Okay, so we want to find the rule for this line here. So normally we'd be writing y equals mx, but this time y will get replaced with v, the m will get replaced with the number we've got from over there, and x will get replaced with t. So we're going to get v is equal to 2,000 t. Again, we replace the vertical variable with the v, we've replaced the horizontal variable with the t, and we'll replace the gradient with either this rate or this. There's the same thing. Part D, so we're going to use this rule here to find the volume after 1.5 hours. So all we need to do is replace t with 1.5. That's going to be equal to 3,000. Because it's a volume, that will be in litres. Part 2, the time taken to fill 5,000 litres. So this time we know that the V, the volume, is 5,000. That's going to be equal to 2,000 times the time. Dividing that through, we're going to get 2.5, or 2 hours 30 minutes, whichever you prefer. Given it's such an easy time, 2.5 hours would be sufficient there. So either 2.5 hours or 2 hours 30 minutes. Okay, this graph shows how far a bike travels over 4 hours. So in 4 hours they've travelled 40 kilometres, so they're just dawdling. Okay. Rightio, state how far the bike has travelled after 1 hour. So we just find 1 hour here, read off that, we'll get 10 kilometres. After 2 hours, you can see they've travelled 20 kilometres. And in each case, all I'm doing is going from the time, going up vertically till I hit the line, then coming across horizontally till we find the distance. Similarly, after 3 hours, that would be 30 kilometres. Write down the speed of the bike, so the rate of change of distance over time. And again, that's just the gradient. So you can see that they've travelled 40 kilometres in 4 hours. So we can say the speed is 40 kilometres divided by 4 hours. 40 divided by 4 gives us 10, and that'll be in kilometres per hour. Find the gradient of the graph, exactly the same thing. The gradient is equal to that rate of change. Exactly the same question, but it's important you need to that you understand that. What do you notice about your answers from B and C? They're the same. It's a bit of a funny question, that last one. Okay, the rule linking the height of a plant over time is given by h equals 5t, where h is in millimetres and t is in days. Find the height of the plant after 3 days. So we simply replace t with 3. We can say h is equal to 5 times 3. And that's equal to 15, and remember the height is measured in millimetres. Find the time for the plant to reach 30 millimetres. And again, if it's growing by 5 millimetres per day, so well, I guess we could substitute in if you like, but common sense says 5 times what is equal to 30, so t is going to be equal to 6. Let's just do it that way. Similarly, to reach a height of 10 centimetres, remember that's 100 millimetres, so 5 times what is equal to 100. Again, we'll get 20 there. Okay, if we need to complete a table for that, each time we just take that value of t and multiply it by 5. We complete this graph. Okay, so we don't have a scale up here, so we need to, and again, this is where I should have brought a actually, let's try different amounts there. Okay, so what I'm going to do here, we want to go up as high as 20. Let's spread that out a bit more. Okay, look, we don't need to graph all 4 of these points, just graph the first one and the last one. Then very carefully with your ruler, draw your line through there, so that's h is equal to 5t. Find the gradient of the graph, and again, look, it's just going to be the coefficient of t in this case there. Okay, we've got a 300 litre fish tank. It takes 3 hours to fill from a hose. Must be a very slow hose. What's the rate at which water is poured into the tank? I say. So for part A, so the rate is just simply going to be the amount of water that goes in divided by the time. That'll be 100. Now we've taken the number of litres, divided it by the number of hours, so that's in litres per hour. Part B, we're going to draw a graph from 0 to 3 hours, so just pardon me while I bring in I've just realised that's not going to work then. Oh yeah, if I put it just there, then we'll still be able to read the next questions. Okay, so we want to go from 0 to 3, so let's do something like that for time. Okay, and up the side we want to go up to 300 litres, so let's call that 100, 200 and 300. So we know it starts at being empty. After 3 hours it'll have 300 litres into it. Luckily for us it goes through, notice our line passes through each of these junctions there. Okay, so we can see that graph there. So the gradient of that is just going to be that same thing there. I mean, we could pick any 2 points there. Say, for instance, those two. We've got a rise of 100 and a run of 1. 100 divided by 1 gives us 100. But again, we could have just picked it from that number there. Okay, so a rule for V. So, sorry, that was V. So we can say V is equal to the gradient times that horizontal variable. Okay, we want the volume after 1.5 hours, and we've been told to use this rule rather than the graph. Okay, so the volume after 1.5 hours would just go 100 times 1.5, which will be 150, because that's a volume, it's in litres. And the time to reach 2,000 litres, again, what we're really doing is we're solving 2,000 is equal to 100 t. So dividing through there, sorry, that should be 200, not 2,000, sorry about that. Let's just get rid of that one. So 200 is equal to 100 t. Dividing through by 200, we'll get t is equal to 2. Again, that's going to be a time, so that will be in hours. A solar powered car travels 100 kilometres in 4 hours. What's the rate of change, i.e. the speed? So we just simply take the distance. So speed is equal to the distance divided by the time. 100 divided by 4 is 25. We've divided by the kilometres by the hours, so that's in a rate of kilometres per hour. Not surprising for speed. Okay, we're going to draw a graph. We need to go across for 4 hours. We need to do 100 kilometres, so let's go say 20, 40, 60. It's only just going to fit on. Okay, so 4 hours, they will have travelled 100 kilometres. Okay, so what's that going to? Let's go 2 to 50, so I can sort of roughly keep on line. I'm determined to get a ruler from school this afternoon, or from the news agents. Okay, so we've done part B over there. So part C, the gradient of the graph is the same as the speed, so m is equal to 25. And the rule for D will quite simply be, again, this is going to be distance there, and that was time on that axis there. So the vertical axis D is equal to the gradient times the horizontal variable. Okay, the distance after 2.5 hours, so distance is just simply going to be the gradient times 2.5. That'll be 62.5. It's a distance, so it's in kilometres. The time to travel 40 kilometres. So again, we replace the t with we replace the d with 40. So we've got 40 is equal to 25 times t. Dividing both sides by 25, we're going to end up with, I better just check it before I embarrass myself. Yeah, so we've got 1.6 hours. Now that's a weird amount of time, so let's press the degrees, minutes, seconds button on our calculator, and we're going to get 1 hour 36 minutes once we interpret that.